Welcome to The Explainer. Today, we're pulling back the curtain on the science that makes sure everything from your car to your coffee is made just right. We're talking about the tools behind consistency and quality.
You know, it's not magic, it's statistics. The real secret is all about understanding and then controlling something called variation. Those tiny natural differences that happen in any process. Okay, let's dive right in.
Think about it. In any process, whether you're baking a cake or, building a rocket, there's always going to be a little bit of natural variation. I mean, no two things are ever exactly the same. And managing that reality, that is the absolute key to quality. Right? Because if that variation gets out of hand, quality just plummets. You end up with products that don't work, services that fail, and really unhappy customers. So the goal here is to build a toolkit, a set of methods to measure, model, and finally control this variability. That's how we make sure things work as expected, time and time again. So where do we even start? Well, before you can control anything, you have to be able to see it, right? And that brings us to our first set of tools, which is all about making data visual. So put yourself in the shoes of a quality engineer. Your job is to watch the thickness of a special coating on hundreds of semiconductor wafers. Every hour, you get a new flood of data, and it looks something like this. It's just a sea of data, a total wall of numbers. Can you spot a trend in there? Is the process stable? Is something going wrong? Honestly, it's pretty much impossible to tell just by looking at it. Not very helpful, is it? But what if we could turn this chaos into a picture? And boom! This is the power of a simple histogram. We've taken that exact same sea of data and just grouped it into different buckets. All of a sudden, we've got clarity. We can see the shape of the data, we can see where it all clusters, that's the center, and we can see how spread out it is. The whole story of our process is right there in front of our eyes. Or, for a different kind of snapshot, we can use something called a box plot. Now, this little graphic is incredible. It packs in what's called a 5-number summary of the data. You get the minimum, the maximum, the median, and the quartiles, all in one clean, simple image. Here, for example, we can quickly see the variation in the diameters of holes being drilled in an aircraft wing.
Now here's where it gets really interesting. We can use these plots to make big decisions. What you're looking at is quality data from 3 different manufacturing plants. Just by glancing at it, which plant do you think is performing the best? See, plant 1 has the highest quality on average, but look how spread out it is. It's also the most variable. Plant 3 is way more consistent, even if its average is a little bit lower. These plots just make complex comparisons totally intuitive.
Pictures are fantastic for getting that gut feeling, but sometimes we need to be more precise. We need to boil things down to a few essential numbers. It's like taking the data's vital signs. So let's move on and see how this builds on what we can see.
First up is the one we all know and love, the mean, or, the average. This tells us the central tendency of our sample. It's the one single number that best represents the typical value in our whole data set. Now, don't get hung up on the formula itself. The key idea here is to think of it as the point at which the histogram exactly balances. So imagine our histogram from before was a real physical object. The mean is the exact spot where you could put your finger underneath it to make it balance perfectly. It's the data's center of gravity. Okay, next we absolutely have to measure the spread, that variability we keep talking about. And the most important tool for that job is the standard deviation. The best way to think about it is like a special ruler that just measures how consistent your data is.
A small standard deviation? That's great news. It means your process is consistent, it's predictable, and everything is tightly clustered around the average. A large one, though, that means your process is all over the place, spitting out a huge range of outcomes. Controlling quality, a lot of the time, is really just a game of shrinking that standard deviation.
All right, so we can see our data and we can summarize it with numbers. Now it's time for the really big leap. How can we use what we've measured in a small sample, say 100 semiconductor wafers, to make smart predictions about the entire process? We're talking thousands or even millions of wafers we haven't even made yet.
This is where we go from describing what has happened to modeling what could happen. And we do this with an amazing concept called a probability distribution. It's basically a mathematical model that acts like a crystal ball, telling us the likelihood of seeing any specific outcome from our process.
Now, these models come in 2 main flavors. On one side, you have discrete distributions. These are for things you can count, like the number of defective parts in a box. You can have 0, 1, or 2 defects, but you can't have 1.5 defects, right? Then on the other side, you've got continuous distributions. These are for things you can measure, like weight, thickness, or temperature, that can take on any value within a given range.
And you can really see the difference right here. Discrete distributions look like bar charts, with a specific probability for each separate outcome. Continuous distributions, on the other hand, are these smooth curves, where the probability is actually the area under the curve between 2 points. Now, there are tons of these distributions out there, each one suited for modeling different kinds of processes. But let's do a quick, rapid-fire tour of the 3 biggest ones, the greatest hits you'll find in the world of quality control. First up, you have the binomial distribution. This one's perfect for simple yes-no or pass-fail situations, like counting how many chips in a sample are bad. Then there's the Poisson distribution, which is great for counting defects over a certain area or a period of time, like the number of blemishes on a roll of fabric. And finally, the undisputed superstar of statistics, the normal distribution.
Ah, the bell curve. You've seen it everywhere, and for a very good reason. It is so powerful because a huge number of natural and manufacturing processes just happen to follow this pattern. This model lets us calculate the exact probability of seeing certain outcomes. For instance, a manufacturer can use the bell curve to figure out the odds that a paper grocery bag will be strong enough to do its job.
So what makes the normal distribution so special? Well, it's this kind of magical idea called the central limit theorem. And don't let the fancy name scare you. This quote sums it up. It basically says that when you take a bunch of different random things and add them all up, the result tends to look like a bell curve, even if the individual things you started with didn't. It's why the bell curve pops up everywhere and is just so incredibly useful.
So if you take one thing away from this whole explainer, it's this simple, powerful 3-step process. First, you visualize the chaos. Turn that wall of numbers into something you can understand, like a histogram. Second, you calculate the vitals, summarize it with the mean and standard deviation. And third, you model the future. Pick the right probability distribution to make smart predictions and keep your process in control.
From the variation in your morning commute time to the consistency of that perfect cup of coffee, the histogram, the standard deviation, and yes, the bell curve, they are everywhere, quietly shaping our entire world. Thanks for joining this explainer.